Okay, so let me start with introducing a bit what SRM is all about, and then I go a bit into pro and cons. So let's have a very short look into how the climate system works in a very, very broad way. So we have the Earth, and the Earth receives nearly all its energy from the sun. And of this light which comes in from the sun, about 30% is reflected right away on snow, on clouds. The rest, so 70%, is absorbed by the Earth and used to warm the Earth up. So most of us goes into the ocean, a bit in the land and the air. So this ensures that the Earth has a temperature above 0 Kelvin, so some non-trivial temperature. And everything that has temperature also emits light, in this case infrared light, so warmth radiation. And in equilibrium, as much infrared light, so that's the dark red arrow, goes out of the system as the sunlight that goes in and is absorbed. So then we would have a constant temperature. Now the Earth has an atmosphere, and the atmosphere does not let all infrared light to go out into space without problem. So part of it is intercepted by the atmosphere and sent back to the Earth. So the Earth needs to have a warmer temperature than if the atmosphere did not exist in order to be able to emit as much infrared as it absorbs from the sun in terms of energy. This is called the greenhouse effect, and a bit of greenhouse effect is natural. Without any greenhouse effect, the Earth would have an average temperature of minus 18 degrees. Before we started to emit CO2, it was plus 14, so that's a natural greenhouse effect. But the problem is that we are adding a bit to the greenhouse effect by adding CO2 and other stuff to the atmosphere. So the Earth has to warm more in order to be able to emit enough infrared to eventually go back into equilibrium again. So now, what is solar radiation modification? Well, we have a problem because we increase this greenhouse gas effect. So the idea is maybe we can also reduce a bit the energy that comes in from the sun, or in other words, let the Earth reflect a little bit more sunlight. So this 30% of sunlight that gets reflected, maybe we could make it into 31% or so to get this energy balance back where we want it to be. That's the idea. A lot of possible techniques have been suggested. Not all of them are feasible or effective. So one of them is very futuristic. Maybe you could have a sunscreen between the Earth and the sun to intercept the sunlight out in space. The feasibility of this is pretty doubtful. Then way more down to Earth, maybe we can just paint a few things white. We can have white roads and white roofs. Well, that's very nice locally to avoid urban heat waves, but it's not very effective on a global scale because there are simply not so many roofs in the world, and we also need them for solar cells. Another idea is, well, we have the Arctic sea ice. Ice is brighter than water, so if we do our best to preserve the Arctic sea ice artificially, maybe that's going to help us reflect sunlight. Here, feasibility is a bit of a question, and also it would probably only have local effects. Now let's get to the more serious ones. One of them is marine cloud brightening, and I'll discuss it a bit in a moment. And another one is stratospheric aerosol injection. I will also discuss this at a moment, so these are the two most serious ones. Cirrus cloud thinning is also doubtful feasibility, and here the idea is to get rid of certain clouds that act as a greenhouse gas. But since it's also considered questionable whether it works, I'm going to not talk much about it. Okay, so let's have a look how marine cloud brightening and stratospheric aerosol injection are supposed to work. Here you see an accidental instance of marine cloud brightening. So you have here ocean water, and then you have these tiny white spots. These are so-called stratocumulus clouds. So these are low clouds which are pretty bright already. And in that field of stratocumulus clouds, you have these white stripes, and they arise when ships are passing underneath the cloud deck. So what happens is air over the sea is relatively clean, so there's not much dust in there. But cloud droplets all need a tiny piece of dust to attach and put the water on. And if there are not many dust pieces around, then you have a few droplets which are big, because a lot of water needs to compete for the same pieces of dust. But if you offer more dust, for example, from the ship's chimney, then you can build more cloud droplets, which will then be smaller for the same amount of water. But a cloud that consists of many small droplets is brighter. It reflects more sunlight than a cloud that has a few big droplets. So the idea here is that we could maybe produce dust artificially by some kind of pump that sprays seawater into the air. So the seawater will evaporate, then a little salt crumb will remain. Most of them will fall back into the sea, but a few of them will be carried up by the wind into the clouds and act as these dust particles. So we've seen from the shipwreck picture that it works in principle, but the details are more complex because the method could also affect the lifetime of the cloud. So if the cloud then sucks in more air from the top, which is dry, this dissolves the clouds, then it could work the wrong way around, right? Because the cloud is brighter, but it also dies more quickly. And it probably depends on the situation, whether these feedbacks are dominant or not. So it's very ticklish business to balance this. And then the other technique, that's the one I work on, is called stratospheric aerosol injection. And this idea comes from big volcanic eruptions like Pinatubo in 1991. So that eruption injected something like 20 megatons, 20 million tons of sulfur dioxide, SO2, into the stratosphere. That's the atmosphere in roughly 20 kilometers height, so above the region where we have our normal weather happening. You see that in the picture. You see these two sort of black heaps there. These are thunderclouds, so this is normal weather. And above that, you have this gray horizontal line. And that is a cloud that arose in the stratosphere because of this eruption of Pinatubo. So SO2 is a gas, but it reacts with water that's in the stratosphere to form sulfuric acid, and that forms cloud droplets. And like a normal water cloud, this cloud will reflect some sunlight. So from the side, in this picture, it looks black, but from the top, from the sun, it looks a bit white. So it reflects sunlight. So here goes the sunlight. The Pinatubo eruption caused a cooling of about 0.5 degree for about 1 year. Why 1 year? Because everything that's in the air and is not gas will eventually fall down. That holds also for the sulfuric acid droplets. They stay for roughly 1 year in the stratosphere and then they fall down. That's much a longer lifetime than if you would do it further below in the troposphere, so where the weather is, because then the stuff would be entangled in rain clouds and rain out immediately, or in a week or so. In the stratosphere, it can live for a year, but not forever. And so the idea of stratospheric aerosol injection is basically, well, if Pinatubo can do it, then we can also do it. So why not just put some special airplanes that can reach the stratosphere, put some SO2 in them, send them up, and let them spray out SO2. And since the stuff only lives for a year, we would need to keep replenishing it. It also means that we could steer it a little bit, because if we think, oh, it was a bit too much or a bit too little, we can change the plan for next year. Is this feasible? Maybe I should say that for the rest of the talk, I'll focus on stratospheric aerosol injection as example, because it seems to be the most likely candidate. If we ever come in a panic situation, we need to do something big, quick. Maybe I'm biased because I research SAI, not marine cloud brightening, so feel free to ask a marine cloud brightening guy to check that. Okay, so is this feasible? Probably yes, but not yet. So you need airplanes which can reach the stratosphere to do this, and normal airplanes don't reach the stratosphere, at least not in the tropical regions, because the stratosphere is higher in the tropics than on the poles. There are airplanes which can reach this height, military airplanes, but they're not suitable to carry a lot of SO2, so you would anyway need to somehow design a new aircraft. So they don't exist yet, but on the other hand, we know in principle how airplanes work. It's not as hard as was, for example, the atomic bomb in the Second World War. So if we want to develop these things, we can develop these things. There's also an attempt to estimate how much it would cost, and there is uncertainty. It could be twice as much, it could be 3 times as much, it could be half as much, but it's a very, very rough ballpark estimate. This one guy came up with something like $20 billion per year per degree cooling. That sounds like a lot, and if the Netherlands would have to do that on their own, this would be a lot. But on worldwide scale, this is less than a per mil of sort of the worldwide production. So that sounds, in that respect, it almost sounds cheap. Like at least it's not financially infeasible. Another question that is also often asked, like, suppose we now get in a panic, climate is tipping, everything goes wrong, when could we start doing it? Well, not immediately, because we will need to build these airplanes. And the guy who came as a cost estimate, he comes from the airplane industry. He likes a nice, orderly approach, no rush. So he says, well, if you're organized, we would maybe take 7 years to design this aircraft, and then we would build a medium-sized factory and gradually build more and more of them. Of course, if you're in a rush, you can build a big factory, spend a lot of money to quickly build a big factory and crank out these airplanes in less years, and then you dissolve the factory. That's not how he likes a nice industrial orderly approach, but of course, if urgency is there, you could do it. So then you would end up as maybe 10 to 15 years. And there's one more catch, because I said the stratosphere is lower near the poles than near the equator. So if you would say we will start to do it near the poles, then you could use ordinary airplanes, rebuild them a bit so that they can eject this SO2 out of them. And then you could, in principle, start earlier, but also not immediately, because there is no suitable airport at the southern hemisphere, which is far enough south. So you would need to build a new airport in the south of Argentina or so. Okay, so SAI is not a small thing. It's a relatively big project, but it would probably be feasible if we wanted to within a few decennia. So after the first decision, if we really are in a rush, it could be done in something like 10 years in principle. And because it's not incredibly expensive, financially speaking and technically speaking, a well-developed, technically fit big country could do it on their own. Whether that's politically what's going to happen is another question, but theoretically it could be done. So SAI is feasible, and it's not that hard to do it somehow. The most difficult part is if you do it to get it right. That's the hard part, not the doing it, but the not getting it wrong. Okay, all SRM is pretty controversial. And as one example, at Utrecht University, where we come from, is a bit of a center of a debate that arose. So Jeroen Oomen, he is part of a group who wrote a letter suggesting that we should stay away from SRM because it's impossible to govern. I'm sure he will tell you why. And then a few other people who are more in the SAI climate physics group, like me, we got a bit annoyed, if I may say so. We found this unbalanced, and we said, well, of course, SRM is risky, but rejecting it is also risky because of the big problem we have with climate change. So we need to balance these more. We need to do more research in order to be able to see whether SRM is a good idea or not. So both groups asked people to join and sign the letter and whatever, so we had a bit of a controversy there. Later on, the two of us also sat down once and said, well, maybe we should figure out not only where we disagree about, but also where we maybe agree about. And that's how I want to, around this, I want to structure a bit the rest of my presentation. So we came up with 5 points we actually do agree about. I didn't ask Jeroen if he agrees exactly with how I phrase the summary, but very roughly we agree here. So our 5 points are as follows. We have a serious problem with the climate system. If you do SRM well, you could probably reduce but not eliminate physical risks. If you implement it in a stupid way, you could make it worse. There are huge political risks about SRM, and every ton of CO2 saved will reduce risks, either because we have less warming or because we need less SRM or something in between. Okay, so let me try to prove these things to you. So I say the climate situation is very, very serious. Here are some CO2 emission scenarios from the most recent IPCC report. And I want to focus on the light blue line, the most optimistic scenario. And you see that emissions go down steadily, and from 2055 onwards, we take out more CO2 from the atmosphere than we put in. So we have netto negative emissions. By the end of the century, in 2100, the negative emissions are pretty big compared to the stuff we currently emit now. So we basically assume here that we can take out a lot of CO2 from the atmosphere, but the problem is we don't yet know if we can actually do that. There are a lot of ideas how to do it, but the question is whether they can be scaled up quickly enough without nasty side effects. So maybe it can be done, but we don't know. Now suppose that we can do it. Here are the temperature predictions, the global warming predictions, if we would follow any of these scenarios. And you see that even this optimistic scenario could bring us to above 1.5 degrees. There's a pretty big uncertainty because we don't fully know how much the climate reacts to CO2. Embarrassing to say as a climate physicist, but there is this huge uncertainty in the climate sensitivity. And then one more thing, suppose we can reach 1.5 degrees, we don't know if that's safe. I mean, it's often framed like 1.4, we are fine, 1.6, we are in hell. But there is nothing that magic about the 1.5 line. I mean, for every tenth of a degree, you increase risk of something going wrong, but whether 1.4 is the limit, or 1.5, or 1.6, or 1.3, we don't know that. So it could very well be that even 1.5 is already too much. And with things going wrong, one thing that I mean is so-called climate tipping points. So the climate system is full of subsystems that are reasonably fine until you reach a certain point, for example, a certain CO2 concentration, and then things go wrong. So one example of this is the Greenland ice sheet. If the Greenland ice sheet starts melting too much, it shrinks downwards, but air gets colder the further you go up. So if the surface of Greenland goes down, it comes into warmer air, so it melts even more. So it goes even lower, so it melts even more. So you have a feedback process that eliminates the Greenland ice sheet. And there's somewhere the critical threshold is hit, and we don't know exactly where. But if you look here at the graphic, it could very well be at or even below 1.5 degrees. So we don't know if 1.5 degrees is even safe. So to summarize, suppose there's no SRM, we would anyway need massive CO2 negative emissions to stay near 1.5 degrees. We don't know if that works. We don't know the climate sensitivity, so maybe even if we're super ambitious, the climate is more sensitive than we think, and we don't know if 1.5 is even safe. Okay, we have a problem. I hope we can agree on that. Next point, a well-implemented SRM program could probably reduce physical risks, not eliminate, but reduce. So there are a lot of modeling studies. Of course, models are not perfect, there are uncertainties, but they relatively consistently point in the direction that my claim is true. So let's have a look at some of these model experiments. So I'll just grab a few of them. And in one of them, they used a CO2 horror scenario, an awful lot of emissions, and then tried SEI to keep the climate as constant as possible, not just global mean surface temperature, but also the difference in temperature between the northern and southern hemisphere, and the difference between equator to pole. The north-south difference is important because it determines the position of the tropical rain bands, which cause the rainforests. The rain in the tropics likes it warm, so if you would cool one hemisphere, the rain would shift to the other hemisphere. So if you shift the rain to the southern hemisphere, you have drought in the Sahel, and that's really not what you want. Okay, so the idea here is maybe that's not exactly the climate targets that you would want to achieve, but it shows that you can handle a few targets simultaneously, not too many, but a few. So there's some amount of steerability in the system. So let's see if they can indeed keep these goals by injecting aerosols at certain latitudes. And here's the results. So first you see in the left plotted the aerosol injections go up and up and up. That's because the CO2 increases, so they have to do more and more of these injections in order to keep temperature constant. To remind you, 20 teragrams or megatons, that was the Pinatubo eruption, so they go above 1 Pinatubo eruption per year. But of course, it's also a very crazy CO2 scenario. And on the right graphics, you see these temperature goals that they told themselves. So the top one is the global mean surface temperature. They can keep it at the target level with SAI, and the same holds for this north-south difference and equator to pole difference. So in model world, at least, it seems that SAI kind of works in a sense of you can broadly define some goals and stick to them. In model world, right? We have not tried this in reality, of course. But can we really get all aspects of our old climate back if we do SEI? Well, here's another set of simulations. So the blue one is a scenario with just CO2, and the red one is a case where they did SEI for 50 years and then stopped. But let's for now only focus on these first 50 years. So global mean surface temperature is nicely kept constant while the SEI is in place. But now, with the same simulation, they also plotted the global mean precipitation, so rainfall and snowfall, and then they got that. So the blue line, that's again the one with only CO2, the global mean precipitation increases, but in the red line, it decreases. So you cannot stabilize at the same time the global mean surface temperature and precipitation. So this means there are always some things which don't exactly fit. Details depend on how exactly you do the SRM. However, it looks like, in general, if you do SAI to reduce global warming, you would probably still push the climate in most regions for significant climate variables closer to pre-industrial. So on this map, you see for certain regions how variables like the mean temperature and mean precipitation, whether they go closer to the old climate or further away if you have global warming with SAI. So blue means you get closer to the old climate, and red means it gets worse, you get even further apart. And let's put it like this, there's way more blue than red in this graphic. So it looks like SAI is far from perfect, you will have some remaining climate change, but it can broadly push you closer to the old climate, which worked pretty well for humanity. There are also indications that these terrible climate tipping points that I mentioned, that the risk of them would probably be reduced for quite a lot of them with SAI. I should say that this is an overview study which we did, but there's very, very little direct research on SAI and tipping. So this is a rough indication, but it's very preliminary. But it makes some sense intuitively, right? Because many of these tipping points, like the melting of Greenland, directly depend on temperature, and temperature is the one thing that SAI is pretty good at pushing down a bit. But yeah, there are also some cases where we really have no idea because nobody has even explicitly researched it. Here's one graphic from my own work. You maybe know what the Gulf Stream is, so that current that brings warm water towards Europe. And that's also under risk of dying under global warming, which would cause here maybe cooling, certainly more colder winters and more winter storms and regional sea level rise. So no fun. And this AMOC current is probably going to decrease quite a bit with global warming. So that's the red line. That's a result from one model. Models disagree a bit on how much that would be, but okay, we will probably see this current weaken. But if we do SAI from 2020 onwards, then in this particular model, the weakening is much less. So that's the blue line. So AMOC remains much stronger. Now, an extra catches, can it at some stage be too late? Can you ruin the Gulf Stream system if you wait too long with the SAI? The answer is, to some extent, probably yes, at least in this work we did. So the green line is a case where we take, again, this horror CO2 scenario, but only in 2080 we think, oh shit, it's too warm, we will do SAI now. And then the temperature goes back to the target level, but the Gulf Stream current, so this AMOC, does not. It stops weakening further, but it does not jump back onto the blue line. So this suggests, and it's a very, very nasty idea actually, right? That this puts some pressure that maybe if we want to do SAI to help the climate, we would need to do this quickly because otherwise we lose something. Well, please never look at one climate tipping point in isolation. There's an awful lot of considerations that you should do if ever considering SAI, but yeah, that's one out of many. Okay, SAI would also have some side effects. For example, it could slow down the healing of the ozone hole. It would not like eliminate the ozone layer, which we all depend on to not get skin cancer, but it could slightly delay the healing of it. It would cause acid rain, which is basically an air pollution. That should be seen in the perspective, the amounts of air pollution of acid rain that we would introduce with SAI is still smaller than what we're already introducing anyway with industrial emissions. But it's also that it's still some concern, right? But this should be balanced against the huge problems of climate change. So it looks for now that these side effects, physical side effects of SAI, should be taken seriously, but they are far less severe than the problems of climate change itself. But we should not forget them nonetheless. So to summarize this part, in at least models, it looks like that a well-implemented SRM program could reduce climate risks quite a bit, but not completely. It's probably technically feasible. It can cool. You would have, however, some residual climate change. It could reduce tipping risks, and side effects are not negligible, but not a game stopper. But I was assuming that we do a reasonable way of doing SRM, like avoiding to cool only one hemisphere, all the other mess that you could do. But would we do it like that? We don't know. So that brings me to the next point. If you do SRM badly, you can make things worse. How can you do things badly? So here's one example. That's a simulation I have already shown. So you see here the red simulation assumes that we do SAI for 50 years and then we stop. And you see how the temperature curve behaves once you stop. It shoots up like crazy to go back to the values of warming that we would have achieved if we had never even started the SAI. So it goes to the values dictated by the CO2, which is still there. People call this a termination shock. So if you terminate the SAI, you get the warming shock that you would otherwise have spread over 50 to 60 years. You would get it in 10 years. And that, of course, makes it way harder for human systems, for ecosystems, and so forth to adapt. Other ways how you can make things worse is, for example, cooling only one hemisphere so that you would shift the tropical rain bands. I've mentioned that already. Or maybe with this marine cloud brightening, which is way more local than SEI. What if you have a lot of local attempts which are interfering each other? I do something to benefit my country, your country thinks that I have messed you up, so you do something to solve the problem, and someone else is going to do something because they think that you've messed them up. And it's like a patient who gets 10 medications for all sort of different diseases, all interfering with each other. And my sister's a doctor, and she says more than 3 medications for a patient is too much, and the same, I think, probably holds for SRM. Of course, in principle, bad implementation can likely be avoided if you assume that decision makers are rational, cooperate globally, are not under too much time pressure so they can consider their decisions, they listen to scientists, they are benevolent, they are cautious, they build up backup capacity to avoid termination shock, and so on. I'm not sure if all decision makers fulfill this category. Okay, I think this was short enough to skip the summary. SRM carries a lot of political risks. Probably Jeroen will say more about this, so I will keep this brief. But among the list of worries is, for example, mitigation deterrence. So what if people say, oh, we have a plan B, we can do SAI, so we can be a bit slower on reducing CO2, we can keep driving our car for longer. Then I said SAI is relatively cheap. It could, in principle, be done by one big country. So what if China or the US says we are going to do that, and the other country, or Europe for that matter, don't like it? Are we going to start a war on them? Are we then trying to emit short-lived greenhouse gases to counter the SAI just because we don't like the idea that they're having their hands on a global thermostat? How about justice? Even if they do it for the global best, do we want others to take the decision for us? How about global south countries? Are they going to have a voice? There are even people who say SRM could be a weapon. Well, it would be a terrible weapon because you can't really take aim. But a conflict expert told me the fact that it's a bad weapon doesn't mean that nobody is stupid enough to try. Make out of that what you want. Ethical concerns. Are we allowed to deliberately play with the climate, to play God? I mean, of course, we already play with the climate because we emit CO2, but that's by accident. Is it different if you do it on purpose than if you do it by accident? And yeah, how could we even govern this? Are we going to set up a global institution? Do we believe that in the current messy geopolitical situation we could do that? On the other hand, how do we govern a world with 2 degrees warming and several climate tipping hit and parts of India becoming uninhabitable because of heat waves, which kill a lot of people? That's also a governance challenge. So maybe there's no good solution. Maybe there's only the least bad solution. Okay, last one. Every ton of CO2 that we prevent will reduce risks. Basically, if we emit less CO2 or less greenhouse gases, we will either have less warming if we don't do SRM, or we will need less SRM to hit the same warming target, or something in between. And so my call to you is, make my work useless. Try to ensure that we don't need SRM. And because asking such a call should always come up with some practical suggestions, here's my list of suggestions. No individual can save the world, not even Greta Thunberg, I'm afraid. But if you want to do something, there's a lot of small things or bigger things that everybody can do. You could reduce your own carbon footprint. There's a very nice book by Mike Berners-Lee called There Is No Planet B. So if you want some practical tips that are not preachy but just nice to read this book and share it. You can persuade others to join. There's a nice book by Per Stockness about climate communication. Maybe that's useful for you. Because if you do something and you persuade 3 friends, who persuade 3 friends, then that's getting more and more. Exert political influence, so take the climate into account when you vote. Maybe join a climate protest. Also something that can be done with not much work is get yourself the newsletters from Greenpeace and all these other environmental organizations and sign all petitions that you think make sense and share them with friends. Or support environmental organizations or political parties who think are doing the right things financially or with volunteering. I'm not your boss. I'm not saying that's what you need to do. I'm just saying that if you want to do something, these are practical hints which are not like asking too much and you can pick what fits you. But I just don't want to leave you without something that you could do if you want. That's it from me.
So when I started doing my PhD on geoengineering, back then this was carbon dioxide removal and solar radiation modification. What I did was I was interested in this larger question, where does this all come from? How did we get to this point where we are talking collectively, scientifically, politically about actively intervening in something as complex as the climate with speculative technologies to solve climate change. Right? When you listen to just the steps that takes, every single step in that sort of trajectory has a history. How did we come to see the climate as something that we could manipulate in the first place? How did climate change become something that we couldn't really solve? How did we think collectively we have the technical capacity or the political capacity to solve these issues? So part of my PhD was a historical work, trying to understand, okay, where does this all come from? And it was really without judgment. I was just trying to understand, okay, so what the hell is going on here? But then my real interest was, how does that history then influence the way that we do science on climate engineering technologies today? So I went around and I interviewed all these people doing research at the time. This was between 2015 and 2018. And this was my very favorite quote. Sometimes I feel like I'm working on the Manhattan Project, because who knows what will happen with this technology. This was a quote by a modeler, a PhD student who later became a good friend of mine. And I think it's the most poignant quote on SRM that you can have. Because what I want to tell here, what I want to think through with all of you, is what if SRM isn't a climate technology, or isn't first and foremost a climate technology, but is really, when you think about it politically, something else, like the Manhattan Project. So my whole investigation, I, at some point, wrote up into this book, if you want to hear more. This is really that investigation of history and sociology, of where does this all come from. Today I'm taking a slightly different route, where I'm throwing up questions about where does this technology sit when it's not in model world. Right? When it's not the models that we're talking about, but political reality. So I'm drawing out all kinds of different trends and moments to have you see, okay, this is really what is happening with that technology. But to understand what is happening with that technology, we need to understand at least practically why it's so controversial. Well, Claudia spoke a lot about a lot of the issues, so I will run through this really quickly. There is a technical question here: can it do what it promises? The honest answer is no one can really know until it is done at global scale. what does that mean politically? Who would control the technology? Which countries or companies hold the power to do this? Who could do this? How could they do this? What will the role of scientists be? Will they be technocratic sort of decision makers, or will they be sidelined immediately for other considerations? Does researching this lead to a normalization and then just saying, well, we're going to do this nonetheless? And specifically, I think the two questions that are central to me here today: what are the consequences of this kind of technology, this kind of research for climate policy, for climate politics at large? And will this technology be part of a larger sort of war over who controls the atmosphere? So, the history of climate science, of climate engineering, and of climate change, you need to understand that they're all connected from the very beginning. So the very first policy document where there was a serious concern about climate change as something that may affect the future of the Earth, or the future safety of the US in this case, was this White House document in 1965, Restoring the Quality of Our Environment. And what is interesting to see here is that, first and foremost, they don't see climate change as a major issue. And if it becomes a major issue later on, well, we'll just do countervailing technological intervention, which was basically the kind of technology that we're talking about today. But even more interesting is if you go back 7 years, you have all this interest, scientific and political, in controlling the atmosphere for wholly different reasons. Right, so in American Weekly, Francis Leighton writes, in 1958, behind the scenes, while statesmen argue policies and engineers build space satellites, other men are working day and night. They are quiet men, so little known to the public that the magnitude of their job, when you first hear of it, staggers the imagination. Their object is to control the weather and change the face of the world. Some of these men are Americans, others are Russians. And the first skirmishes of an undeclared Cold War between them have already been fought. Now, why is this so important? It's because from the very beginning, the funding of climate science was bound up with the Cold War. So the climate science that was built at the beginning was not necessarily built just to understand the climate, it was always to control the climate. And that still has ramifications for the way that geoengineering is being discussed today. And I will run through, again, loose examples and then bring it together at the end for a thesis about this. So how should we then see SRM? And what is this thing that we're talking about? Well, first and foremost, and this is the kind of vision that Claudia just explained, we should see it as a response, right? A reactive fix for climate change, because it is that. The reason we're talking about it today is because we're all concerned about climate change in one way or another. But it works on a certain conceptualization of the climate, and I will explain that a little bit later, and it doesn't really work in others. It works if you have a very one-dimensional understanding of what the climate is. It works less well if you introduce more and more parameters. Now, typically, people say, well, this is a temporary technology that gives us time to organize structural change. But what is structural change? Is it that we're going to be talking about doing this for 30 years while hopefully our carbon dioxide removal technologies are scaling up? And again, we heard Claudia, that's quite speculative. I would say pretty much impossible when you look at it politically and technologically. And what then is it? Or are we talking about 500 years of doing this, or 100 years of doing this? Can we imagine keeping a system up like this for 500 years? Can we imagine the political stability, the technological stability on those timescales? Even 100 years. Can we imagine that? Maybe 100 years from now, the nation state isn't a concept that we use intuitively anymore. That could happen. 100 years ago, half the nations in the world weren't countries. So what does that mean for the stability and the structural change that we're talking about here? So it's not control, it's possibly the lesser of two evils. Is it what is bad? How much does this relate to climate change? And especially, it really looks very good if you have that one-dimensional comparison that we had on the screen earlier, which is valuable. I'm not here to say that that's not valuable, but you can make these technologies look better by reducing complexity. But first and foremost, for me, this is a political technology. It is an infrastructure and a politics that intensifies all kinds of deep-seated political divisions about what the future of the world ought to be. And in terms of political prestige and its ramifications, SRM is in the same category as nuclear weapons. For the prestige of great powers, control over weather and climate is fundamentally of the same category as nuclear weapons. This is why they organized all that research around it in 1940s, 1950s, 1960s, because the person or the country that controls the atmosphere controls, to a very real extent, the future of the world. So it's not necessarily about weaponization, but it might be about weaponization of the idea of control. Now, at the same time, this is a climate technology that is fit into an existing sphere of environmental politics. And this is the question that has absorbed me in the years since I really worked on geoengineering. I started to work on environmental politics at large. What is this thing that we're doing that seems to be so, well, with all due respect, shit? Like, it's just failing. Why is climate politics failing? Why is environmental politics failing? What is the role of these technologies in it? So that became my new obsession after I did my PhD. And so, in that obsession, it became very clear that we've constructed over the past 30 or 50 years an environmental politics that keeps reproducing a captured future. A future that is always sort of the same as the present, and we only sort of allow a bit of rumbling in the margins. We do a marginal change. And there's a whole scientific system that exists to uphold the notion that nothing much needs to change. So our claim here is that the environmental politics that we know cannot deliver. It will not deliver and it cannot deliver. And at the same time, it's falling apart. And that's because it's culturally and materially unable to imagine futures that are meaningfully and environmentally different from the future, or from the present. And it's not simply an inability, it is in the regime of how it's organized. And it is a very specific role that science and technology plays in that, and there's a very specific role that also the promise of technologies like geoengineering or carbon dioxide removal play in that. So in environmental politics, there's the predominance of a discourse, of an organizational assumption that we call ecological modernization. And ecological modernization is basically a compromise between the people who said we need economic development, we need economic growth for prosperity, and the people who said economic growth is killing us. And the compromise is, well, we don't need to give up economic growth as long as we have smart solutions to climate issues, environmental issues at large. So it is fundamentally about the belief that there are positive-sum solutions in which there isn't really a question of winners and losers, but everyone can win. And so part of that debate has been that no one will want to change their lifestyles. Because that's the thing that we're not talking about. We don't want to talk about lifestyles because people are selfish creatures. That's one of the key assumptions that is made in that ecological modernization discourse. Now, where does that get us? In a situation where between 2010 and now, we've had a shift in, just one example, car consumption, like new cars being sold. And then if SUVs now, which really came up around 2010, if they were a country, they would now be the 5th largest emitter on the planet. That is about a cultural aspiration that is somehow not addressed in environmental politics, and that is very hard to fit into the environmental politics that we know today. So the claim then is that there is a sort of funnel in environmental politics that works against transformational change because it is about maintaining the lifestyles, the cultural aspirations, and the ideas of today. And in that funnel, there is a very specific role for solar radiation modification, or for that matter, hydrogen or nuclear fusion, or the speculative promise of a technology tomorrow. Because basically it's a politics of miracles. When I started my PhD in 2015, carbon dioxide removal was basically regarded as a fantasy and as hugely controversial. 3 years later, when I finished my PhD, 3.5, it was totally normalized. I went to a Dutch left-wing Green Party, and I was not allowed to question whether CDR was the future, like carbon dioxide removal. 4 years. It went that quick. So what if people start to realize that this climate politics is also failing? Where do we turn next? That's this technology, because it's the promise that it doesn't need to get that bad. I will say this, none of what I'm saying here is necessarily an argument against SRM itself. Right? I am just explaining how this has a political life. Whether you think we should still do this research is a different question. And some days I wake up saying no, some days I wake up, I'm conflicted, some days I wake up like, God, I'm so scared about climate change, we need to do it anyway. But you need to do it without closing your eyes for this kind of stuff. And so the question becomes, if this is the logical next step, how does that happen? Does that happen through reasoned democratic debate? Or are there other dynamics at stake here? And I mean, by the way that I'm phrasing this question now, it's pretty clear that I think there are other dynamics here. And so what I'm interested in is this question, like, so how do we get to a point where I think if we keep doing environmental politics as we do it today, within 5 years, SRM is a completely normalized part of the suite of responses to climate change. It'll be the next big thing that is necessary. And that won't happen because people say this is what we want. It happens because there are all kinds of venues that work to put this in play. And so there is already a pre-packaging going on that makes SRM sort of ready to put into climate politics. And I'll very quickly run you through 4 examples. They are basically just examples. And then we can have a conversation about that afterwards. But to sum them up, there's depoliticization of this technology through scientific authority. There's the normalization through the political calibration of science. I will get to that in a moment. There's extra statecraft. There's basically sort of statecraft-like decision-making in other spaces that aren't actually governments. And there is commercialization of this technology through startup engagement. And so importantly, in all these issues, it isn't necessarily so much a climate technology as it is something else, right? In the commercialization, for example, it is about a venue for profit making rather than climate. I am going to just go straight into this. What is that depoliticization through scientific authority? Well, it's important to realize that when we engage as the audience, or as just a general public with scientific findings, we don't engage with the very beginning of the process, right? We engage with the norms at the very end. So there are all kinds of moments in between authoritative reports, in this case, that sort of set the way that we talk about SRM before we actually realize that that is happening. And so Arti Gupta and Ina Muller, who are also both in the Netherlands, coincidentally, had this wonderful investigation of, well, there were these two moments of big scientific assessments. What happened then? The first report made it so that, this was in 2009, it normalized first SRM as a field of research and carbon dioxide removal as well. But moreover, it sort of shifted the debate from should we do this to how do we do this within the scientific debate. And so they call that de facto governance. It's not officially governing, but then to get a voice, you need to talk about how do we do this? What is the reasonable way of doing this? What is the just way of doing this? Instead of what they call first order questions, should we be doing this in the first place? Then 6 years later, you get these kinds of reports. And they then say, well, basically, we should view the climate system as a thermostat with two knobs that you can turn. CO2 and radiative forcing. So it's basically the two things that Claudia has been explaining to you. And so it's a further narrowing of the things that you can authoritatively discuss, that everyone then starts to follow, because that's the authoritative report. The right one is the National Academy of the Sciences in the US. The one on the left is the Royal Academy in the UK. So often, when we look at the political function of science in climate politics, it is not necessarily science for society or science as a sort of objective truth that we're searching for. No, it is science for policy. So when we're thinking about these reports, they're sort of prefiguring the way that policy can engage with these questions, because it sort of sets the questions that are reasonable to talk about. But that science, imagine if you are a scientist, right? You're really worried about climate change, as both Claudia and I are. The real thing that you want is for policymakers to listen to you, for political negotiators to listen to you. So what do? You start thinking ahead, sort of, what will they listen to? Am I going to come to them and say, well, we need to just cut all economic growth? Probably not, right? Because the moment you say that, you're like, laughed out of the room, we're never going to get that through. So sort of the scientific cockpit, or the scientific endeavor, starts to imagine what is it that the political world wants to hear, and start to sort of acquiesce to those demands ahead of time. And you can see that most clearly in this normalization through political calibration. And this is an example of that other obsession of mine. How the hell did we get from 2015 carbon dioxide removal is something we don't really want to talk about to 2019? It's just necessary. And that basically happened through this graph. There was much more at stake and much more at play, but I'm going to flatten it all out and say it was all this graph. This is a graph projecting the emissions, global emissions, into the future. Now, if you pay close attention to what it does, you can see that between somewhere 2050, 2060, our emissions globally will go below zero. And by the end of the century, very significantly below zero. Very, very far below zero. Now, these this graph comes out of a collection of, a huge collection of pathways for the future made by integrated assessment models. Integrated assessment models are models that sort of merge the economic, the socio-economic world with the climatic world. I'm simplifying this hugely, but that's what they do. And so what the role is of these models in climate science and in climate politics is to ask, under what conditions can we make climate targets? So what kind of policy do we need to have to go down? Now, the modelers figured out pretty quickly that 2 degrees, and specifically 1.5 degrees, this was all about 1.5 degrees, was not feasible within current assumptions. It just wasn't. So what they put in was carbon dioxide removal. And people have gone around and asked them, okay, so when did you put these carbon dioxide removal technologies in? No one really knows. We haven't really been able to figure out when this happened, but it's probably because they needed something to make their models fit with these targets. So when they started doing all this modeling in 2015, after the Paris Agreement, they started to model, can we make 1.5 degrees? Right? That was the big question. CDR was in there, but the assumptions that they would never question because they were afraid that they wouldn't be listened to, all of them ran with quite significant economic growth. All of them ran with the assumption that there would be linear technological development so that CDR would get linearly better and cheaper into the future, which are both hugely, hugely speculative assumptions because CDR requires a lot of land and it's not as given that that's getting cheaper, let alone that you get that land, let alone that you can do that in a fair and a just way. And there's a whole host of other assumptions that are in there. And so we asked these modelers, so do you think we can make 1.5 degrees? And they said, literal quote, I'm not so sure we can make it, but we can sure model it. And we can always make our models work. And that was something they were struggling with, because they could always give you a speculative sort of image for the future with a lot of CDR in it, but when does it become lying, basically? Right? That was their big question. Now, so there was a phase between 2015 and 2019 that these kinds of policy models normalized CDR, carbon dioxide removal, to such an extent that we all now assume that it is part of the future, right? At scales that there's a whole industry around it. Again, this is not saying we shouldn't do it. This is just saying decision-making around this doesn't happen in a democratic way. And now you get these, my favorite people to hate, oil company CEOs who say, well, many people would like to see the end of fossil fuels, but I'm not in that camp. I just want to see the end of emissions from fossil fuels. Totally normalized. This is Vicky Holub of Occidental Oil. And then being able to say, well, we can keep doing this for 60, 70, 80 years. So it also, then that whole normalization gets its life of its own again in political reality. Importantly, and so again, this is my sort of historical obsession, geoengineering is also a combination of a particular way of relating to nature. Right? It's a result of a very specific scientific infrastructure, and I've sort of shown you bits and pieces, and I don't have the time to really go into that. But it is really a holdover of those things that we discussed in the 1940s, 1950s, 1960s about controlling the climate. And you can see that very clearly in the way that for an institution like the International Standards Organization talks about geoengineering, or SRM. And so here we get to the extra statecraft. Now, the International Standards Organization is a private organization. It is a coalition of standardization organizations that are all private, that are in every country. And they all come together in the ISO, and the ISO standardizes basically everything, right? From the line that this microphone is made of, the thickness of the credit card that you have in your wallet, to what a USB-C is, to what anything, really. And that makes sense, right? You need to have agreements about it, because how can you otherwise have a globalized world? But in recent years, they've also started to standardize all kinds of other things, like management standards, or what is good climate policy for a company? They used to have one. They still have it, because their intervention failed. They had one that was based on CO2. But then some companies started saying, well, but that's not a good measure of what our climate impact is. Because a way better measurement of what our climate impact is radiative forcing. Because we might also do all kinds of things that make the Earth cooler instead of warmer. And so for the people who understand this intuitively, what that basically means is we can offset our CO2 emissions with other crap we're putting into the atmosphere. Right? If we're also emitting sulfur, we're making the Earth cooler, right? So what can an aviation company say? Well, look, we're also cooling the Earth down. So radiative forcing-wise, we're sort of stabilizing. Now, as if that isn't really scary enough, the real ploy here, the real fear was that it was a way to make a sort of business model around SRM, right? Because imagine you have a radiative forcing standard. All of a sudden, it makes sense to start selling solar credits, right? SRM credits, radiative forcing credits, however you want to call them, cooling credits. Now, this failed because there were, luckily, people in the negotiations who leaked it because they were terrified and they thought it was a terrible idea, and there was a whole uproar. This was Paris France, the French press. Germany was really angry. So it failed, and it never became a standard. It became a guidance, so you can sort of ignore it. But the idea to commercialize SRM is definitely there. And my other favorite people to hate on in presentations like this is Make Sunsets. I think also Claudia is not a big fan of these people. It's basically two cowboys who have started to sell cooling credits. And when they started selling them, they said, well, for $10, we can sort of cool as much as 1 ton of CO2 emissions. On their website, they have a list of people they have sold their credits to, and they call it a list of geoengineers. We've already made 300 geoengineers in the world, so they're doing a really good job at selling them. So I think this is kind of beautiful. I use it as a background all the time. But the important thing, right, is that's not innocent. Because when we think about the way that politics works, and especially these days, I think it's very intuitive for all of us to realize that politics doesn't just happen in institutional venues. Politics is spectacle. Right? Imaginative technological solutions can be super intense spectacle. And again, these are these two guys in this very glossy photo, where this is what they're doing, right? They're selling themselves really well. So you get all these venues where SRM plays its own role, where it's very hard to say, okay, so where's this going? So I will leave you with 5 theses about this. Some of them overlap with what Claudia's saying. Some of them are sort of my own fears. Some might be speculative. Some you might agree with, some you might hate. On a purely technical level, I actually think SRM might work. But out in the real world, it certainly won't. Because if it is a technology that has so much prestige attached to it, there will be jostling over who gets to control it. There will be all kinds of people trying to get in on the action. There already are all kinds of people trying to get in on the action. But more importantly, even if that were thinkable, decision-making about SRM will not primarily be about the climate. It's very easy to mistake this as a climate technology, but for the US military, this is not a climate technology. For these guys from Make Sunsets, yeah, they present it as a climate technology, but it's a way to make money. For the ISO or the oil companies, it is potentially a distraction from other kinds of climate technologies. And SRM, there's no way around this. It will inevitably get mixed up in a toxic cocktail of conspiracy theory, of geopolitics, of military interest. Conspiracy theory is already there, and I don't know how many of you have heard about chemtrails. We, from time to time, get emails. The most visible researchers on this get death threats because people say you're already doing this. So it is a perfect technology to fit into all of the fears. There is no way around it, too, that it will be used in some way as a tool of climate denial and delay. I'm not saying that will be the main thing, but people will do it. So that means that, to me, SRM is much more likely to be a tool of maintaining a particular status quo by the people in power than it is something that is used to safeguard the lives of the poor and vulnerable. It may play out that way, potentially, but that will be sort of the side effect of the thing that they're actually trying to achieve. So my real, and this is, I thought about this morning and I find it really strange, but I think my real claim is this. If we keep doing climate politics the way that we do it, within 5 or 10 years, this is going to be a normal part of climate politics, and then it's going to get pulled into every weird direction. If climate politics falls apart completely in the next 5 or 10 years, it's up for grabs, for better or for worse. It's not unthinkable that climate politics as we know it falls apart because there's so many pressures from all kinds of different ways. It might be that if it all falls apart, there isn't this force that propels it into the mainstream and it stays connected to the conspiracy theories that are already trying to ban it in the US because they think the government is trying to control them. But it might also be that if the whole climate politics falls apart, that people just start doing it. I just don't know. It's a very uncertain space. It's not a very hopeful story. But it is the way that I feel about this technology, and I'm really curious to see, Claudia, how you think about everything. She was complaining at the beginning, I have to do all the hard work of actually explaining it, and then you can do half an hour of opinions. It's true, I'm sorry. Thank you for listening.